streams to do what is called beamforming. So I will talk a little bit more about beamforming in the next slide, where it will become a little bit easier to understand. But the basic idea is, in this massive MIMO system, in the 0 to 6 gigahertz, sub 6 gigahertz range, the beamforming is done digitally, where you can tune the antenna to, or direct the antenna to look in a particular direction to receive a signal, or transmit the signal in a very in a very specific direction. Now, obviously, you might, as you might imagine, having 1024 streams of data, 1024 antennas, 1024 radios, power amplifiers, etc., you can imagine that the hardware gets very complicated very quickly. Okay, so I don't expect most people to implement 1024 antennas, but probably stop at about 256, at least in the first try. Obviously, all of this is on the base station. On the cell phone side, you may have a maximum of maybe 4 antennas and 4 systems. So that will already give you a lot of gain over the traditional LTE. The other aspect, which I will talk about in the third part of the talk, is what is called full duplex communication. So if you look at any traditional wireless communication system, the antenna, one single antenna, is used by both the transmitter and the receiver. Okay, so you can see this arrow coming into the antenna shows the receiver. The arrow going out shows the transmitter. It is the antenna is reused by splitting the access either in the time domain or the frequency domain. Okay. Now 5G in the second and third versions, in future versions, is going to have the option of doing what is called full duplex communication. In other words, both the receiver and the transmitter use the exact same frequency band, as well as operate at the same time. So obviously, compared to traditional systems, this instantaneously theoretically doubles the available bandwidth. Okay, but obviously, even if you are able to get advantages of up to 80% additional data speeds, that is just spectacular, as you might imagine. Okay, I will come to this aspect of 5G in a few minutes. So the last aspect of 5G that I want to point out is operation in the millimeter wave band. Unlike the massive MIMO in the sub 6 gigahertz bands, in the case of millimeter wave, there is most probably going to be only one or maybe not too many radios. So maybe the 5G standard allows, I believe, does not have a specification on the number of radios that can be used. But I expect that on the cellular side, most people will have a single radio stream and multiple antennas, as you can see here. On the base station side, maybe up to 4 or 5, radios. The biggest advantage is the availability of huge amounts of bandwidth, right? So unlike in the sub 6 gigahertz range, where spectrum is very, very hard to come by, in the in the 28 gigahertz bands, 40 gigahertz bands, 60 gigahertz bands, there is a lot of contiguous bandwidth available. Now the thing is, a lot of these bands are actually used for applications in military and in space communication. So sufficient care will have to be taken to make sure that you do not interfere with those types of uses, because those types of uses are the primary uses that have been historically applied to these bands. Now, the other interesting thing about these bands is that the attenuation through the air is extremely high. So the path loss, such high path losses, means that you will need to put out a lot more power, okay, through each antenna than you did in the 3.5 gigahertz, 700 megahertz, etc. bands. Okay, but this also means that interferers are rare, right? Because not many users, and path loss is very high. So the any interference power will be much smaller than in the sub 6 gigahertz bands. Now, there are several challenges, but primarily path loss is one big challenge, but also components are very hard to come by. They're also very expensive. And building a millimeter wave radio is not easy at all, right? There is a critical block here that is used for beamforming that is called a phase shifter. Okay, the phase shift millimeter wave phase shifters are extremely hard to come by. They are definitely not available readily. So an example of a 3D beamforming system would look like this. So basically you electronically tune the phase shifts of each antenna stream coming in so that the antenna pattern looks like it is focusing in a particular direction. And the base station might have, here I have shown 3 arrays of antennas at 120 degrees so that it can talk to 3 different directions at the same time, multiple users in each of these directions. You will have beamforming in the vertical plane and the horizontal plane. Okay, so you can look up into buildings, you can look down, etc. So obviously this will also require things like, acquisition of contact between the base station and the cellular user. So you can now start to imagine different scenarios. So obviously you are initially searching for the beam, then you do a coarse alignment, then you do a fine alignment, and eventually you start to transmit. So that is kind of what people envision this type of communication the way in which this type of communication will happen. Now, before we go ahead to the next part, right, which is the India specific scenario, I wanted to point out the timelines and resources worldwide. So if you look at 2020, we have almost finalized the, I believe by June 2020, the first version of the 5G standard has been finalized. So deployment is going to start, was due to start in 2020 and probably has started in some parts of the world. But because of COVID, we probably expect that this will kind of spill over into 2021. And the bottom portion shows the approximate amounts of money through both public and private means that have been spent by different countries or unions or so for example the European Union has spent close to $800 million, and so has China. US has spent about $400 million. South Korea has spent about $1,500 million, etc. Right? So this will come a little bit later. I will talk when we talk about the India testbed. So 3GPP is the organization of companies that get together and build a standard, but the standard has to be ratified by the International Telecommunication Union, which is a UN body, okay, where countries have representatives in ITU. 3GPP has representation from companies. As you might imagine, ITU, starting from 3G onwards, they have taken direction from 3GPP as to what standards should be chosen for the cellular communication. So you see that participation in 3GPP is very important to drive the direction in which the cellular technology goes. Since India has historically not had a very large set of companies that participate in these trials or have been able to participate, it has not had a lot of involvement in this except at the country level. However, starting from 5G onwards, we have a big involvement with 5G, and I will point out what is so special about this. Now, if you look at the Indians, application of cellular communication in India, there are some very stark differences compared to what the companies which are involved in building the 3GPP standard experience, right? Most of these companies are from Europe or USA, or maybe from East Asia, right? Japan, Korea, and nowadays China. Now, if you compare to Europe and USA, where a majority of the companies come from, the Indian cities have much higher urban population densities compared to these types of regions. The other thing is that rural deployments in India are quite different from what is envisaged in these types of countries, and I'll touch upon these in the next couple of slides. Finally, there are two other very important aspects. Number one, the technical channel models that are used to develop these standards could very well depend on where these channel measurements are made. Obviously, because the channel, the air that is being used to, the environment that is being used to test is quite different in India versus the many of the temperate regions of the world. And finally, it turns out that Indian data usage patterns are quite different from the rest of the world. Now, if you look at the ITU, so now we are slowly entering the second part of the talk. If you look at the ITU usage scenarios, broadly, you have test scenarios for EMBB, Enhanced Mobile Broadband, Massive Machine Type Communications, which is IoT, and ultra reliable and low latency communication. And what we are interested in is EMBB here. And as you can see, there is an indoor hotspot option, there is a dense urban option, and there is a rural option. Now, what happens is ITU decides the test configurations, the frequency spectrum, the bandwidth, data rate, etc., where the use conditions under which the system will be tested. If you look at all of these, the what we are primarily interested in, for example, the rural case, you will find that the rural case in 3GPP and ITU basically models a high-speed vehicle passing through rural areas, right? So in other words, imagine a car going in a highway from Los Angeles to San Francisco, or from New York to Washington, DC, right? And so on. They will be passing through large swaths of rural areas. They'll be going at very high speeds, maybe on a train or in a car, right? And this scenario models that. Obviously, we know that this has nothing to do with the actual situation in rural India, right? So now you can see the motivation for why India should specifically drive aspect. This is one example of where India should drive, test use scenarios and the standard, right? For example, almost 50% of Indian population, if 5G goes without taking them into account, you will be basically not be addressing half the population in India, right? So one of the big motivations for building an India-specific use case is to address those types of scenarios. So starting from 2016-15 onwards, Indian academia and some companies have been attending 3GPP standardization meetings, and they have developed a particular scenario called low mobility large cell, or LMLC. So this scenario is going to address the large rural populations of India. Okay. And there are specific aspects of it. I'm going to, in the next couple of slides, I'm going to tell you how they came about these types of standards. If you look at the Indian villages, primarily they get their high-speed internet through the gram panchayats, where the optical fiber backhaul lands. From those gram panchayats, there are villages around those gram panchayats which get their can potentially access high-speed internet through the optical fiber backhaul. Okay, if you look at the gram panchayats, India has about 2.5 lakh gram panchayats and about 6.5 lakh villages. Now, we assumed a base station at the center of the gram panchayat, which then addresses the closest villages to that gram panchayat. So to do this, what you have to do, we obtain the list of all gram panchayats and villages, okay, from the government database. From the Google Map API, we determine the latitude and longitude of each one of these, and we associated each village to its closest gram panchayat. So that will help us design the radius of the cell. Okay, and it turns out that if you use cells of different radii, you will cover larger and larger number of, as you increase the cell size, you will cover more and more number of villages. And this plots the distribution of the distance between the villages and the closest Gram Panchayat. It turns out that for a 6-kilometer radius, you will cover 95% of villages, with the mean being 2.7 kilometers. This is the combined CDF across all of India, okay, covering most of the big states. Okay, so it looks like the radius of 6 kilometers is the ideal size, cell size, to cover rural Indian users. Okay, now the basic architecture, as I've shown, is going to be like this. Now, what the 5G community in India has done, involved in the 5G testbed, they have created a specific scenario called LMLC, which has now become part of the 3GPP 5G standard. Okay, and this has been submitted and accepted in 3GPP as one of the scenarios. And interestingly enough, there have been a lot of developing countries in Asia and Africa which have taken on this model, understood it, and realized that it can address their needs also. Okay, normally the way it works, the 3GPP 5G standard is, we added the Indian enhancements, and then this was ratified in the ITU meetings. Okay, and more specifically at the modulation level, LMLC is going to use, remember that in the rural scenario, it is quite possible that because the cell size is larger, okay, it covers a larger number of villages, but each one of these users are not expected urban users, right? And they will not be moving at very high speeds. So you also need to design a specific kind of modulation to cover those types of users. So specifically, LMLC rotation has a 90-degree rotation. Okay, what is interesting about this is, with appropriate baseband filtering, the peak to average power ratio of the RF signal, okay, is much lower than the typical 5G signal. So this means it turns out that the lower the PAPR, the more power that the PA can put out, and higher will be the efficiency of the PA. Okay, so in India, pi/2 BPSK will be mandatory for the LMLC use case. Across the world, for the sub 6 gigahertz, it will be optional, but for the millimeter wave case, it will be mandatory as long as the network and the cell phone can handle it. So for the first time, a truly Indian technology is part of the 5G standard. So that kind of completes the second part of my talk. The third part consists of a specific IC implementation of one aspect of 5G. So as I will cover in the testbed part, the last part, I kind of wanted to end with the description of the testbed. You will see that there are several different organizations, academic institutes, research organizations involved in 5G, in the 5G testbed and in R&D for 5G. And several of them are doing work on integrated circuit development also. And I am presenting one aspect of that, which is full duplex communication, kind of a next generation research for next generation of 5G. So the exact frequency of operation 2.5 gigahertz is not so critical, because we chose it because it is easy to find components that operate at these frequencies, antennas, etc. And it is also because the 2.4 to 2.5 gigahertz wireless band is an ISM band, industrial, scientific, and medical band. There is an unlicensed access to that frequency band, and that is the reason for this choice. So if you look at conventional transceivers, so I'm kind of, this portion of the talk is quite technical, right? So if you look at conventional transceivers, you have a transmitter and a receiver. with two different nodes. So for example, in the case of cellular communications, either node 1 or node 2 could be a base station, the other could be a user mobile. Okay, obviously the signal is very large at the transmit antenna on the transmit side, on the two sides, and very small by the time it reaches the receive antenna. Now on each of these nodes you have the receiver and the transmitter competing for access to a single antenna, right? This particular case shows what is called TDD, or time division duplex, where the TX and RX operate at different times. So what you need is an RF switch that switches the antenna between the TX and the RX. So standards such as Bluetooth and wireless LAN operate with TDD. The other type of transceiver architecture that is popular is FDD, or frequency division duplex, where both RX and TX can operate at exactly the same time, but they use different frequency bands so that they don't interfere with each other too much. But that means that you need a block here that does appropriate filtering to remove the unwanted signal. So for example, on the RX side, you need to filter out the transmit signal. This particular block is called a diplexer. 3G and 4G are examples of FDD systems. For example, GSM standard was time division duplex. Now, full duplex transceivers aim to design systems that can use the antenna for both TX and RX at the same frequency and at the same time. So in other words, the transmit and receive frequencies are exactly the same. So obviously this duplexer element is extremely important because it needs to make sure that no part of the TX reaches the RX. So some common duplexer elements are shown here. So the first of these is what is called a circulator. The circulator makes sure that the TX signal can reach the antenna. The antenna received signal can reach the RX, but you have very good isolation between TX and RX. And it gives you about 20 dB isolation, but the real problem is these are extremely narrowband and bulky. So you cannot use them for portable mobile communication. The other interesting thing is that the isolation of these circulators is highly sensitive to the matching at the antenna port. And as many of you might know, the antenna impedance can actually change depending on various aspects. The other type of duplexer element that has become common for mobile systems is what is called the hybrid transformer. The hybrid transformer gives much better isolation, but it is highly narrowband in nature. Okay. The advantage is that it is integrable in CMOS technologies. You can get rid of the narrowband nature by trying to tune some of these impedances, but there are still some aspects that are lacking in the hybrid transformer application of hybrid transformer application to full duplex systems. So some of the most common duplexers are based on the concept of electrical balance. So basically, you try to create balance between two paths going from the TX to the RX. Okay, and when you take the difference between those two paths, the TX signal is effectively cancelled. Now, obviously, in this case also, the frequency dependence is of these impedances will affect how much isolation you get. In this specific work, we have used a capacitive bridge-based duplexer. Now, as I pointed out, fundamentally, the cancellation is narrowband. In the case, I'll go back to the hybrid transformer because that is important here. In the case of the hybrid transformer, the isolation is fairly narrowband, and tuning it requires tuning at the fourth port. But that tuning matches the antenna impedance to get cancellation. That does not necessarily always give you wideband operation. Number two, the tap of this antenna port, for example, cannot be varied. So the transformer is what it is. The primary, secondary, and secondary inductances and the mutual inductances are fixed. A capacitive based bridge gives you a huge advantage through the use of reconfigurability of the capacitance values. So you can, in CMOS technologies and in bipolar technologies, it is extremely easy to build a bank of capacitors along with switches to create a variable capacitance over a wide range of values. So in this particular bridge, under the balance condition, the ratio of capacitances has to be equal to the ratio of the antenna impedance to the balancing impedance. So I'm going to call this K here because I'm going to point out the use, how this K can, or what happens when you vary this value of K. So in our particular implementation, this shows the block diagram of our implementation of our overall receiver, the self-interference cancelling receiver. You can see this is the, I hope all of you are able to see my mouse. I'm using it to point. This portion is the bridge that causes actual cancellation. This is the antenna port and this is the balancing impedance. As you can see, C1 and C2 are made reconfigurable inside the chip. And because the output is coming as differential, we are doing differential to single-ended conversion using a transformer. Okay, and that goes into a fully single-ended receiver. So this receiver was fabricated in a 130 nanometer CMOS process. And as you can see, the duplexer is fairly almost, 70% of the area of the rest of the receiver. The total area is about 0.7 millimeter square. So now if you set K equal to 1, so in other words, the ratio of capacitances is 1. This particular plot shows the Tx to Rx isolation as a function of frequency. Now, as you can see, at a particular frequency, when the impedances are exactly matched, the bridge cancels almost by more than 60 dB. Okay. If you look at a 20 megahertz bandwidth, which is a typical configuration for LTE and Wi-Fi, the mean isolation is about 55 megahertz. About 55 dB. This is the Tx to Rx isolation. For wider band signals, it of course gets lower and lower. Now, what we realized is that many of the data networks are actually asymmetric. So for example, in many cases, the download rate is much higher than the upload rate. The download requirement is much higher than the upload data rate requirement. So if you look at two full duplex nodes, having a tunable tap point is extremely useful because you can now bias the data network, bias the duplexer such that you get high data rate in one direction and low data rate in the other direction. This leads to an asymmetric link. So what we can do, we can tune the insertion loss through the tuning of this parameter K, the capacitance ratio, such that the insertion loss in the TX path, for example, at low K values, the insertion loss is lower and lower on the TX side, but the noise figure is higher and higher on the receive side. So you are biasing the bridge towards the TX side. If you choose K ratios larger than 1, you would bias it in the other direction. And largely you can see that the sum of noise figure and isolation remains constant. And this and the next slide show the third order intercept points. So the measured antenna to receive IIP3 is about minus 4 dBm, which is pretty standard for a cellular and Wi-Fi receiver. And with cancellation, you can see that the TX to antenna IIP3 is extremely high. It's about 50 dB, plus 50 dBm. And this shows the frequency response, across the 2.4 to 2.46 gigahertz band. This shows that the receiver, and the proposed, idea is fairly robust over a large band of frequencies. So to summarize this technical portion of the talk, to our knowledge, this is the only known work, full duplex work with tunable TX-RX insertion loss. And the way we designed it, because we started working on this before the 5G standard was set, we show that it meets the A22.11G standard, which is A and G standard, which is the Wi-Fi standard for a 20 megahertz bandwidth. This, of course, assumes that you get an additional 50 dB cancellation on the digital side, which is pretty standard for most of these full duplex systems. So with that, we come to the fourth part of the talk. Hopefully, I'll try to keep this short because we are coming to the, we are running out of time. We have another 10 minutes or so, I think. So I'll try to cover the India testbed in this part of the talk. So this 5G testbed was first proposed by Professor Arogyasamy Paulraj of Stanford University, probably about 7 or 8 years ago. And in its present avatar, it is funded by the Department of Telecommunications, the DOT, and obviously without their funding and support and guidance, this testbed would not be a reality. So obviously, we have to acknowledge, it's very important to acknowledge both DOT and Professor Paulraj. Coming to the specifics of the project, this is a 240 crore project which started in 2018, April of 2018. It is a 3-year project and the mandate is to build and demonstrate an end-to-end 5G testbed, complying with the latest 5G standards available. The goals of the testbed are actually several. So obviously, there is a strong requirement to create R&D capability in India, right? And you will find that R&D capability multiplies in effect in many different expected and unexpected ways. So for example, if you develop this R&D capability, if even a few of them go out and start telecom startups, that will really kind of jumpstart the 5G economy and the 5G R&D situation in India. More specifically, the 5G team has developed and is in the process of demonstrating specific solutions for India. This was one of the mandates also. For example, I talked about LMLC, and there are a few other applications that are, that are going to be India specific. And finally, just like China did so in 4G, this has really kickstarted India's participation in these global fora, right? So 3GPP, ITU, IEEE, etc. Because what we have clearly shown through our participation is that there are very specific Indian cases, Indian scenarios, which are not covered by existing standards. And this kind of shows the timeline. So if you see the funding and project started way back in 2015 through a project by the Ministry of Electronics and Information Technology, MeitY. And that has been, you can imagine that as phase 1 of the 5G development in India. The second phase was funding was taken over by the Department of Telecom. So that is the ongoing phase right now. So between 2015 and 2018, we evaluated pre-5G. We looked at release 14 of 4G. We looked at what are the technical performance requirements. We held lots of workshops, discussions, etc. And we also attended all the 3GPP meetings. And starting from 2018 onwards, this has evolved into 5G technology proposals from India. And what has happened is that has gone into the 5G standards and back into IT for evaluation. And what I will just point out that there have been over 60 patents in 5G technologies from India covering various aspects of the 5G standard. And more than 120 contributions have been submitted to 3GPP. LMLC is going to be an important part of the rural portion of 5G. It is going to be mandatory in India and for in both the sub-6 gigahertz and the millimeter wave bands. And in in other parts of the world, it is going to be mandatory for the millimeter wave frequencies when both the mobile and the network are capable. So I'll kind of skip this slide because of paucity of time. What I wanted to point out, I wanted to list the various organizations that are involved in 5G development in India. As you can see, IIT Bombay, IIT Hyderabad, IIT Madras, IIT Delhi, IIT Kanpur, Indian Institute of Science are the major academic institutions involved in the 5G testbed. Apart from that, Ministry of Electronics is represented through SAMIR, which concentrates on antenna and electromagnetics. And Center for Excellence in Wireless Technology, or CIVIT, is an R&D organization associated with IIT Madras. At the end of the testbed project, once the testbeds are fully developed, we aim to see different testbeds located in different parts of India, as shown on this map. So as you can see, IIT Delhi, IIT Bombay, IIT Hyderabad, Indian Institute of Science, and IIT Madras and CIVIT are going to host testbeds. Now, each of these testbeds is going to be unique in a particular way. All of them will not be identical. Each of them has concentrated on different aspects of the testbed. For example, IIT Madras has concentrated on the hardware platforms and the core network. If you look at IISc Bangalore, they have concentrated on IoT, baseband algorithms, and Li-Fi, and so on. Right. So I'll just point out that each of these testbeds is not going to be unique. Currently, there are about 40 investigators, faculty members, and senior researchers, and over 200 researchers, project associates, project staff working on the testbed. Part of building having a broad vision and building such a testbed is engaging with Indian telecom companies for various aspects and subsystems of these hardware and software platforms. For example, the testbed, set up at CIVIT and IITM will look something like this. So you will have, this shows a couple of base stations, which the front hall will consist through an eCPRI wired link. The baseband cards will do processing of hundreds of megahertz of bandwidth worth of data, and then the L2, L3 will happen separate from the baseband cards, and so right. And as you can see, I have shown some aspects of the standard here for the 3.5 gigahertz band. There are going to be 64 antennas. There will be 100 megahertz bandwidth occupied by these by these signals. We'll have the millimeter wave base station will have 256 antennas operating at 28 gigahertz. Now that might change to 26 gigahertz. The bandwidth, RF bandwidth, is 400 megahertz for the millimeter wave bands. This will also cover LMLC with a bandwidth of 20 megahertz. The backhaul, the L2 and L3 can interface with the IIT Bombay core, for example, and there are other aspects that I'm not covering here. So probably I think I have covered all of this. I'm kind of going to skip this here, but because I've covered various aspects of this in the different slides leading up to this slide. The subsystems will include massive MIMO, which is the sub-6 gigahertz band, and the millimeter wave radios. We will have the 5G baseband, which will be 5G new radio standards compliant. It will support both lower bands and higher bands. It will consist of Cloud RAN, full duplex radios, the core network, IoT, security, Wi-Fi, and and so on. And finally, once this testbed becomes a reality, we should ideally be able to access many of these testbeds from different parts of India if required. Right, so we will probably support, will most probably support remote access as well for specific aspects. Obviously, if you are testing hardware, it may be a little bit more difficult, but there are certainly many aspects that can be tested remotely. And the idea is that the 5G testbed should support various types of users, including academic institutes, but also telecom startups, operators, equipment companies, and the application and solution developers. So this testbed, once it becomes a reality, will support various variety of users. So I'll kind of summarize my talk here and stop. So my talk consisted of 4 parts broadly. The first parts gave an introduction to 1G to 4G cellular communication technologies, and listed and maybe told you a little bit of little bit of detail about the key technologies, key aspects that are new in the 5G standard and why it is called the 5G new radio. In the second part of the talk, I specifically concentrated on the Indian rural scenario, where a new technology or a new aspect called low mobility large cell using pi/2 BPSK has been accepted in the 3GPP standards and in the ITU standards. In the third part, I presented one specific piece of research work that happened in our group at IIT Madras on full duplex communication. Full duplex communication is going to be an important technology that is being considered for the next revision of the 5G standard. Finally, in the last 10 minutes or so, I gave you a quick overview of the 5G India testbed. Who are the users working, which are the institutes working on this, what is the history of this project, and what the end goal is. And I wanted to acknowledge Professor Radhakrishna Ganti, who is kind of overseeing a lot of the hardware, network, software, network, all kinds of aspects at IIT Madras, and the rest of the broader 5G team across all the organizations. And finally, I wanted to acknowledge MeitY and Department of Telecom for funding this project over the last 6 years or so. If you have any questions that you are not able to ask me here that you come up with later on, if it is anything about the RF IC development, IC specifically IC related, you can contact me, you can email me. If you have more questions about the hardware development, on the testbed on the baseband side at a higher level, you can contact Professor Ganti. If you are more interested in the India specific technology, LMLC, pi/2 BPSK, etc., you can contact either Dr. Radhakrishna Ganti or Dr. Kiran Kuchi at IIT Hyderabad. Both of them are experts in this aspect of 5G. With that, I'll end my talk. I wanted to thank all of you for patiently listening to me for a long 1 hour talk, and also thank, of course, the organizers for it.
Thank you, Dr. Aniruddhan. It was a really useful talk because we gave a full spectrum of whatever is happening in India currently with 5G, and that was very useful for us. So now I will move on to some few quick questions before we close the session. So first question is, you mentioned that for LMLC you use the pi/2 BPSK technique. So why BPSK? Why can't we use any QAM techniques? Because that will be more efficient, right?
Okay, very good question. So maybe I'll move to that that particular slide before covering it. Just 1 minute. Yeah. So this is the pi/2 BPSK. Now, point is the if you want, see, remember that the cell size for LMLC is larger than the traditional cell size. The cell size for normal cellular communication is typically of the order of 2-3 kilometers. The cell size for LMLC is going to be larger because the mean cell radius that covers 95% of villages, the radius is 6 kilometers. Now, naturally, that means that has two aspects now. The minute the cell size is larger, on the uplink side, you need to increase the range of the transmitter, which means more power needs to come out of the transmitter while maintaining the signal quality. Obviously, more power can be pushed out with existing power amplifier technology only by changing the waveform. If you look at more modern waveforms such as quadrature amplitude modulation, QAM, the peak to average ratio is actually quite large. Whereas BPSK, especially with this type of filtering, has much lower, peak to average ratio. And that enables you to increase the effective power coming out of the power amplifier because you can push it closer to saturation so that you can extend the range of the cell. I hope that answers the question.
Yeah. So next question is then. So can we say that at the sub-6 gigahertz we are mainly trying to achieve the higher data rates at a lesser bandwidth, whereas at millimeter wave we are trying to go for a larger bandwidth, apparently around some 400 megahertz?
Okay, very good question. So I'll go back to that specific those slides. So that is indeed correct. So maybe I don't have it here. Maybe it is. I'll cover the just 1 minute. I think it's here, it's listed here. So at 3.5 gigahertz, there is 100 megahertz bandwidth, whereas, in the millimeter wave bandwidth, there is 400 and probably higher also if required. That is correct, but with a caveat. So the reason the sub-6 gigahertz is capped at 100 megahertz is because of availability of spectrum. Spectrum is already very densely used in this frequency range. You do not have more than 100 megahertz very easily available. So you increase the data rate by having a large number of transceivers, up to 1024 transceivers. So the data rate is with a smaller bandwidth, you increase it through larger number of spatial streams. In the case of millimeter wave, there are not that many users right now and the range is shorter. So you have larger groups of contiguous bandwidths. So therefore, you don't need many spatial streams. Okay, typically it is expected that for a single user, you will use only one spatial stream. So even though you may be using large number of antenna elements, each of them will be driven with the same RF data stream, except that they're phase shifted. So with 400 megahertz, you gain the same number of data rate, same amount of data rate, or rather not same data rate, but a large data rate because you have bandwidth available. So that is the technical reason why the frequencies and systems have been chosen in this particular manner.
Okay. So next question is why hybrid beamforming has not been considered, as the digital processing needs to be augmented by analog processing to reduce the number of RF hardware. Can you please elaborate?
Yes. So let me go to that specific sub-6 gigahertz slide. Just 1 minute. Yes. So hybrid beamforming indeed would ease the requirements, but the issue is adding additional complexity to the hardware, because remember now in massive MIMO you are going to have 1024 RF chains. So the minute you need to do hybrid beamforming, you need to add additional analog circuitry 1024 times. So the idea of not choosing that is to keep the complexity of the RF to a manageable extent. Right. So if you need to have phase shifters and amplitude VGAs and so on in the RF path to include hybrid beamforming, that would increase the power consumption, that would increase the area, that would increase the size of the base station. So with that in mind, they have opted to do only digital beamforming. Naturally, it is quite possible that if this becomes a reality in the next versions of 5G. So normally every generation over the period of 10 years, they revise the standard and add more options. It is quite possible that you would get you would get hybrid beamforming in the more advanced versions of 5G.
Okay. I think we'll have the last question. Is there any possibility of using cognitive radio systems, to avoid the interference, as you told, with the primary users? Can we explore that possibility?
So that is kind of in general, the idea of cognitive radio is to do that, is to avoid interference with already existing signals. Now, in my mind, I don't see a direct application to 5G systems, except for the fact that in the sub 6 gigahertz range, right, there are lots of bands here which are already being used for 4G and 3G and so on. So naturally, in all such scenarios, cognitive radio has application. I don't see a specific relevance to 5G. I'll put it that way. In my mind, I'm not able to see a specific relevance to 5G. Cognitive radio in general always has potential application.
Okay. So thank you so much for all your answers, sir. It was a great pleasure in having you. Thank you for accepting our invitation also to give a talk in our workshop. So with that, I think we have come to end of this session, and for all the participants, the next talk is happening in another link which you would have received in your mail. So kindly log out from this, and you can log in into that link, and you can the link is already open. So we'll have Prasad Bhatt, who is the CTO of Astro, giving the talk there. So you can all log out from here and log in that link. Will start at 6:30 p.m. So Aniruddhan sir, if you can turn on your video, maybe I'll take a screenshot of both of us together.
Sure.
No, hi sir.
Sure.
Yeah. So if you can go back to your first slide, it will be useful for me.
Yes, of course. Just 1 minute. Oops. Yeah. Do you see it?
Yeah, I'm seeing it. So, but I'm not seeing your face.
Oh, I see. You wanted to capture with the first.
Yeah. So, thank you so much for the talk. It was great hosting, and it was very useful talk for me too. I mean, I gave a detailed overview of what exactly is happening in India, which I don't think people who are working in this only will be able to tell. So that's great to have you, sir.
Thank you so much. Thank you so much for inviting me, and I was glad to give this talk here.
Yeah, so if it's possible for you, you can join the other talk starting at 6:30. If it's possible for you, you can join it there.
Sure, I'll try to join.
Yeah, thank you, sir.
Thank you. Bye.